Okay, now we are going to make it even simpler. Because I know you want life to be simple. Okay, so let's make it simpler for you even. Okay, now for a round shaft, remember this is emphasis on the word for round shaft only. Okay, just now is any shape. But for round shaft only, the effect of the stresses along the y-axis is ignored to further simplify the analysis without sacrificing much of the accuracy of the analysis. Okay, the accuracy is not compromised. Okay, and yet the calculation becomes so simple. Okay, somebody try to use this simple equation. He want to use finite element. Okay, after all the hard work, even the value is not very accurate. Okay, so actually, if you have done finite element, you know that this to determine the what this what boundary equation this what is what is uh what forgot lah what is it what is to determine all the loading. Okay, this thing I forgot it. Long time I'm not using that. Right, is not as easy as it seems. Okay, I used to be very good with finite element last time when I was still working. Okay, now hence, okay, for round shaft only. Okay, we will make it into a single dimensional analysis. Remember, I emphasize for round shaft only. Don't use this for rectangular or square or anything else. Okay, hence this problem round shaft only became unidirectional analysis. The resulting principal stress and maximum shear stress become sigma 1, sigma 2 is equal to sigma x divided by 2 plus minus sigma x squared divided by 2 squared plus tau xy squared. Squared. And then tau 1, tau 2 is equal to plus minus, okay, sigma x divided by 2 squared. So if it involves round shaft, straight away use this equation if you need to find the principal stress. Okay, this should be the principal stress for you to use. Remember, okay, when it round shaft, just do this one. Forget about the one, okay, the previous one. This one, forget about, definitely you must forget about this one. Okay, forget this one. Okay, so any problem so far? Okay, so now life is here. You want to make your life simpler? No. That is as simple as it can be. Okay. Now, okay, I make a bit simpler also somehow. Okay. So we make a simple definition of ductile and brittle metal because why? When you have to do your calculation and you are having tests, right? In the test, you have to determine how are you going to decide which failure criterion to use. Okay, first of all, you have to decide which failure criteria to use, and then before you can decide that, you must decide whether the material is ductile or brittle. Okay, now how do you know whether the material is brittle or ductile? Okay, so this is the shortcut I've made for you. Okay, for this class. Okay, for this subject only. For this subject only, right? When you are working in the industry, your senior will have method for you to the table. The table usually the manual will show you what would be brittle and what will be ductile. So don't have to worry about it. But this one to make it simpler, I have make it into a three condition. If this condition is met, then it is ductile. If this condition is met, it is brittle. If it is not met, then it is called ductile material. Okay. So what constitute brittle material? The first thing, if in the text of the text in the question, it mentioned that the material is cast or forged specimen. Okay, it's the word. If it said cast or forged specimen, then it is brittle. Okay, I repeat. If it said cast or forged specimen, then the material is considered brittle. One. Number two, if the text instruct the use of MNST for failure analysis. So at the end it said use MNST for failure analysis, then you must know that you are talking about brittle material. Because why? MNST is only for brittle material. Okay? Now the third one, if the text mention that the material is brittle, okay, if the text here the material is brittle or the brittle material, okay, so it's so very clear the brittle material, and then you add the downside that you later put it as ductile. I cannot say your your bad luck lah. Okay, so the text refer is a brittle material. The material is brittle, so of course it is brittle. So under these three conditions, then the material is considered brittle. Okay. Now brittle material is not very popular in analysis because it's quite complicated. Okay. But anyway, if this condition is met, then you must consider the material as brittle. Otherwise, if this is not met, any three is not met, then otherwise all other material are considered ductile. Okay. So if it's not mentioned one of these three, then the material is actually ductile. Okay. 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 So if there's no problem, don't forget this one. Okay. So you forget this one. If you put ductile as brittle, then the answer is you fail. That's it. Just fail. Okay. Now the first failure theory. It is called the maximum normal stress theory. I'm not going to go deep into this one because you have studied it in solid mechanics. Okay. In fact, you have gone very deep. Since we are what we're going to do is going to apply only. So I'm not going to go deep into this one. So what happened is this one is suitable for brittle material. It is not a safe theory for ductile material. What happened is that if you apply this for ductile material, which of course in solid mechanics you use for all material, okay, the result is the safety factor will be too high. If you use this for ductile material, you discover that the safety factor is too high. So what you think will be a nice sport car will be so strong, so heavy, it become a military tank. Okay, if you use this for ductile material. Okay, so cannot. For brittle material, you must use MNST. Okay, for ductile material, you can use the other. Okay, so this is MNST. Okay, so this is the diagram. Okay, showing the region of MNST. I'm not going to go through this one. Okay, you can take a look at here and then take a look at Hibla. It's all given there. Okay, yes. So what I want to show you this one. This is the simplified equation. Okay, that you are going to use inside this class. Okay. Maximum normal stress theory, MNST. Okay, if sigma 1, sigma 2, sigma 3 are principal stresses at the critical point in component due to applied loading, then if sigma 1 greater than sigma 2 greater than sigma 3, then failure. This is the failure criterion. This is the failure theories. MNST failure occurs when sigma 1 is equal to SUT. So as you can remember, right? When you do the principal stress, there will always be sigma 1 and sigma 2. One of them will be tensile, one of them will be compressive. Okay, remember, one of them will be tensile, one of them will be compressive. Okay, so because of that, you have to decide whichever one. So most of the time, by virtue of the question given, sigma 1 tend to be tensile. Of course, this could be reverse. Sigma 1 could be compressive, sigma 3 could be tensile. But most cases, you find that sigma 1 is tensile and sigma 3 is compressive. Okay. Now, if sigma 1, okay, we assume that sigma 1 is the most tensile and sigma 3 is the most compressive, then if sigma 1 is greater than SUT, what is SUT? Ultimate tensile strength. So if sigma 1 is greater than SUT, or if sigma 3 is less than SUC, okay, sigma 3 is less than SUC, means that the value sigma 3 higher value than SUC, because sigma 3 is negative, SUC is negative. So of course, that's why even though it say sigma 3 less, but actually the magnitude will be higher. Okay, because that's negative there. So if sigma 3 is more negative than SUC, what is SUC? ultimate compressive stress, then failure occurs. Okay, take note. So this is the criteria. If you are asked what constitute failure for MST, then you have to give this statement. Okay, sigma 1 is greater than SUT, sigma 3 is less than SUC. What is sigma 1? What is sigma 3? Then you have to explain what is sigma 1, what is sigma 3. Okay, now if you want to include, what is this? Okay, never mind. Okay. Sigma 1 can also see as 1. Sigma 1 is less than SUTFS, but I'm not very good with this one. I don't use this one. Okay, but I use this one. Okay, or is I want you to remember this one. This will be the one that you should remember all the time. Okay, this is it. This is the criteria for failure. So if you want to explain to people, use this one. But when you do your calculation, then use this one. This equation, this one should be your equation. Okay. Fifth safety factor of S. Factor of safety is equal to SUT divided by sigma 1. Okay. Or F is equal to SUC divided by sigma 3. This is negative value, negative value. SUC is negative, sigma 3 is negative. So Fs SUT divided by sigma 1 or equal to SUC divided by sigma 3. Okay. Then you calculate the value. The value is 1, then the safety factor is okay. Okay. So you calculated that SUT is equal to sigma 1, then Fs is equal to 1. So the design is safe theoretically. Okay. Similarly, Fs, if SUC divided by sigma 3 is equal to 1, then theoretically means that the design is safe. That's it, theoretically. Okay. In real life, you wouldn't want a design. Okay, you will use it inside a car that's driving at high speed when you know safety factor is 1, right? Because why? What happens if some extra load is being applied? Okay, a bird flying on the top suddenly crash into your car because that's now safety factor is equal to 1, so it now becomes 0.99999. Okay, so what happened? The car will collapse. Okay, so in real life, you do not use safety factor equal to 1. Mostly you will use maybe 1.25. Okay, even sometimes 1.15, but most, let's say you see 1.25, 1.5. So basically we use 1.5, 2.0, maybe 3.0, 4.0, and even sometimes up to 10.0. Okay, safety factor can be 10.0, especially when you are doing design for solar. What is outer space? Okay, so the Apollo or all those Apollo, they use safety factor of 10 and higher. Why? Because there is so many unknown. Okay, they cannot determine all the forces acting on this rocket, right? So they have to play safe, very very safe. Okay, so that is the problem why it's so very expensive. Okay, so for our case, if we are very very sure all the loading that will be applied, we know for sure, then you can use 1.15 or 1.25. Okay, now 1.15 and 1.25, right, still needed, because why? Sometimes the material themselves are not as 100% perfect. The material, maybe there are some problem in the material, right? Okay, which we do not know, or something due to fabrication. So we still have 1.15 or 1.5, even though we know all the forces that will be applied. Okay, understand? Okay, let me see. Oh. Okay, so now, so please take note. So try when you talk about MNST, try to use this equation. Okay, try to use this equation. Okay, Fs equal to SUT by sigma 1 of SUC. So as long as you remember this one, okay, you cannot go wrong. Okay, of course, calculating this what is sigma 1 and calculating sigma 3 is your nemesis. Okay, your sigma 1 and sigma 3 is your nemesis. You know what is nemesis? It's your worst enemy. Okay, like what is our badminton player? Who's that? Okay. Who's our top badminton player now? No, the second previously. Come on. Badminton player
Lee
last time.
Chong-wei.
Lim Chong-wei. Okay, Lee Chong-wei. Okay, his nemesis is what?
Lin Dan.
Lin
And
Dan.
Chen
Dan.
Long.
Yes, these two, they are two worst enemy for themselves, right? So this is so to me, your nemesis will be sigma 1 and sigma 3. Calculating sigma 1, sigma 3. Okay, the failure criterion that I just taught you is so simple. This equation, see, Fs, this equation. As long as you don't forget this equation, you are totally in control of M and ST. Okay, so that is not a problem. You calculating sigma 1 and sigma 3 is the problem. Okay, if your solid mechanics is not strong, or your equilibrium analysis, everything is not strong, okay, then everything become meaningless. Okay, so the failure criterion which I'm teaching you is actually very simple. Okay, they have made so simple so that designer don't struggle, okay, to find the answer. Okay, so this is the first one, MNST. So let's go to the second one. That is called maximum shear stress theory, or call it TRESCA. Okay, TRESCA is modified in 1864, validated 1900. Okay, so it's being applied, and you can see here, this is the graph region. This is stress region. Okay, now this is something you has probably gone through. Okay, so if not, it should go through lah. Hibla is given there. Okay, but this is the equation that you are going to use. Maximum shear stress theory, MSST.
I'm from
Okay,
Bangladesh.
the failure criterion state that failure, failure state that failure occurs when maximum shear stress, failure occurs when maximum shear stress exceed the shear yield stress in pure tension. This is the failure criteria. So if they ask you what is the theory behind maximum shear stress theory, then you say that the failure occurs when maximum shear stress exceed the shear yield stress in pure tension. Okay, or you're going to give lecture to your workers later to use this one. Okay, so basically what is the easier term will be, and the one that you should remember most of the time will be, safety factor is SF. This is for calculation. SF is equal to SSY divided by tau max. Okay, SF is equal to SSY divided by tau max. Okay, tau max is calculated from Mohr circle, principal stress, right? So, and SSY, what is SSY? Shear yield strength. So this is shear yield strength. Okay, this is shear yield strength. Okay, so what I have is that SSY is equal to 0.5 SY. What is SY? What is SY? SY is yield strength. This is taken from the table. You get from the table, value SY, then you can get SSY is equal to 0.5 SY. Some book, if you read some book, they use SYS, which is basically the same. Say, okay, shear, because why SYS? Shear yield strength. Okay, this one is shear yield strength. Okay, so this one is shear, the small one is shear, this is yield, strength is at the back. Okay, some book is, this is shear, this is Y yield, and then S for strength. Okay, so it's the same, SSY or SYS is equal to 0.5 SY for MST. For MST, SSY is equal to 0.5 SY. Okay, you'll find that for some cases, SSY is equal to 0.788 SY. This is when you are using DET, which you're going to use later. Okay. So for MST, SSY equal to 0.5 SY. So you apply this one, safety factor will be equal to SSY divided by tau max. So if it's equal to 1, design is safe. Okay, theoretically, when you say that SF equal to 1, design is safe, or you can use this one also. Okay, but this one is more convenient to use this one. Okay, more convenient to use one. Okay. Any questions so far? It's not something so difficult, correct? Not something so difficult. Okay. Any question?
No.
No. Okay.
So far so good.
All clear, Doctor.
Oh, clear. Good. Okay, now this is the third one, distortion energy theory. Okay, these are all the three behind this distortion energy theory. Okay, you can get it from Hibbeler. Okay, I have no intention of explaining this one. because you most probably cover it in solid mechanic. Okay, and as I mentioned just now that see for DET, SSY here is equal to 0.577 SY. Okay, okay, for DET, remember SSY is 0.577 SY. Okay, this is already covered in solid mechanic. Okay, and this is the region for this one. It is an ellipse. It's an ellipse. Okay, so what I want will be this one. Okay, the simplified equation. So this will be the, okay, now take note that the DET is most popularly known as von Mises-Henke equation. Okay, von Mises-Henke equation. Engineer always said about von Mises stress, von Mises stress. Okay, when you discuss your stresses, okay, when you go to practical, if there is stresses involved, they talk about MPa, they're talking about von Mises stress. Okay, now von Mises stress is definitely for, as you know, for ductile material. Okay, for ductile material. Okay, but actually it's being applied to almost everything, to all steel. It apply to all steel. Some people may think that steel is brittle. No, steel is not brittle. Okay, maybe high speed steel is brittle. Okay, what most of the rest of steel are considered as ductile. Okay, now the theory based on ductile on distortion energy is known as von Mises-Henke. Von Mises-Henke. So the von Mises stress for 3D analysis is one. The first one. Okay, this is the one. Okay, this is the one. Okay. Okay, and then for 2D analysis is this one. And then you also have for round shaft. Take note for round shaft. Okay, what is this? Sigma prime. Sigma prime means von Mises stress. Okay, sigma prime is von Mises stress. Sigma prime is von Mises stress for round shaft. So sigma prime is equal to sigma x squared plus 3 tau xy squared. So that make it very simple. Okay, so DET calculation is actually very simple. Okay. Okay, now yielding for as far as criterion is concerned, okay, yielding will occur when sigma prime greater than SY. That's it. Okay, failure will occur when sigma prime is greater than SY. Okay, so that is the criterion. Okay, the criterion. So for simplicity, it is simple. Safety factor is equal to SF is equal to say SY divided by sigma prime. That means that if this one equal to 1, safety factor is safety factor is considered safe. Okay, safety is guaranteed. Yeah. If it's less than 1, then of course it's talking theoretically. Yeah. Okay. For real life, it has to be higher than 1. Okay, but as far as concerned, okay, theoretically, as long as SF is equal to 1, the machine is not not considered fail. It is considered as lasting and safe. Okay, so this is the ET. Okay, the ET or called von Mises stress. Okay, so this is the comparison between DET and MSST. Okay, you can see from here that this DET is larger. Okay, because it's larger. Okay, this one, as you can see, MST is very tight. And because I think by virtue of this, the graph is trying to explain to you that MSST is more conservative. Okay, more conservative than DET. More conservative. What means conservative as old fashioned, correct? Nah? Old fashioned, right? So conservative means you mean like more old people type. Okay, old people type, what they are very safe, correct? Not okay. If they drive car, they drive very slow. Okay, so that means what conservative. So this MST is very conservative. So it's not recommended for you to use when you are using your calculation design. You must use DET. Okay, DET is most reliable, sufficiently good. Yeah, and as you can see, engineer use them in the industry. Okay, so the equation is this one: SF equal to SY divided by sigma prime. Very easy. Okay, okay. So basically, we have covered 3 of this failure criterion. Okay, so after this, we are going to do one exercise. Okay, I'm going to show you a demo. Okay, a demo of how you apply this thing. Okay, before we go into that, Do you have any question you want to ask? No question? So everybody understand very well. Okay, this is the one that we are going to do. Where is it? This one. Is it too small now? Okay, this is the one I'm going to do. Okay, so I give you what is 3-minute break. Okay, give you a 3-minute break since you are in the house. You most probably want to run to the kitchen to have a drink or something like that. 3-minute break, and then we proceed with this one.
Alright, Doctor.
3 minutes only, yeah.
Right, Doctor.
Okay. I need a new chair. Okay. Can we proceed?
Yes, Doctor.
Okay.
Yeah.
Yes, Doctor.
So you have this one. Okay, this is something that you have done. Okay. Most probably it's very simple for you all. Okay. But just bear with me. We continue this one. Hopefully, for those who do not may have forgotten. I assume some of you might have forgotten. Okay, there will be our revision for you. Okay, now we have this. Please open up. It's given there. Okay, open up the statement there. What is the statement there? Okay, the statement said that stress critical element at A and C. Okay, so there is a round shaft, so there is a critical element. So here, okay, so in analysis of a beam, the stresses at the critical element A and C are as follows. So A and C, this is B and this is D. Yeah. So the bending stresses due to P, okay, it's not mentioned what is P, but the bending stresses is sigma BE is equal to 350 MPa. Okay, this is one. Okay, and shear stress sigma AX is equal to 180. So due to F is equal to 180 megapascal. So shear stress that is why equal to 100 megapascal due to T. Okay, so torque is 100, actual stress is 180, sigma bending is equal to 150. Now, there is no transverse shear stress. Okay, now because as I mentioned, we do not consider transverse shear stress anymore. Okay, so it become without saying. So you can put aside whenever you do your calculation, you can say, we assume that transverse shear stress is negligible. Okay. Okay. Now SUT is equal to 680. SUC 1430 MPa. Okay. SY 590. So I don't know whether you're familiar or not. So when you are doing your solid mechanic, you only talk about SUT. Okay. You only talk about SUT. I don't think you are because I seldom talk about SUC. The reason is very clear. SUT is equal. SUT is equal to SUT in magnitude. Of course, SUC is negative, compressive. Okay, but SUT is equal to SUC, okay, in magnitude because your analysis involve metal. Okay, most metal, okay, for most metal, SUT is equal to SUC. That is why there is no need to mention SUC. All you need to calculate is based on SUT and you know failure will occur or not. Okay, so that is it because of metal. Okay, now when you use other material other than metal, then you find that the SUT and SUC are not the same. For example, like cast iron, okay, like cast iron, okay, you find the SUC is probably 2 to 3 times higher. Okay, there are materials where SUC is up to 6 times, okay, higher than SUT. Okay, then that's what for let's take a look about concrete. Okay, how strong concrete has very strong. Concrete has very strong compressive stress, but have very small tensile strength. Are you aware of that? Okay. Now, in some design, they use steel beam, right? Totally all steel beam. Okay. Some people they use concrete. So, question you may ask that is it possible because steel is stronger? Not necessarily true. Okay. Most people they use complete steel because they want to do it very fast. They want to design. They want to construct the structure very fast, so they use steel structure. Okay, complete steel structure. But if you want, you can also use the concrete. But as far as concrete is concerned, the compressive stress is comparable to steel. Okay, but the problem is concrete has very low tensile strength, and that is why you find that inside the concrete there is a lot of this steel wire meshing, right? Steel wire meshing. All right. Now this you find that all this wire meshing inside the concrete beam is only for one purpose, and that is to take the loading of tensile. Okay, whenever there is a tensile load, this beam, this wire, okay, this with this steel wire, okay, steel wire will carry will support all the tensile loading. Okay, when it comes to compressive loading, then the concrete will support. Okay, will support the compressive. And see for building, right? For building, there are a lot more compressive loading than tensile. Okay, so of course you know that the compressive stress of concrete must be very high. Okay, okay, understand? Okay, so because of that, now you can see that here in this case that SUT 680, SUC is 1430. Obviously, this is something like most probably cast or special. This is not steel, normal metal. Okay, okay. So once you have know this one, then let us do a question. Okay, if the shaft is cast iron, okay, correct. The shaft is cast iron. That's why the SUT and SUC is different value. Okay. Safety factor is put at 1.2. Okay, who decide the safety factor 1.2? That will be the engineer. Okay, that will be you lah when you are working, right? When we are doing the design, somebody will ask, okay, what safety factor we are going to do? Okay, and everybody will look at you, right? And then you what you look? You want to look at everybody else? No, you have to look at yourself. Okay, if you do not know what's the answer, you will melt there. Okay. Okay, so the engineer, like you all, will decide what will be safety factor. Okay, but that's not to worry because you have a lot of manual in your backup, so you can just refer to them and they'll give you the answer. Okay. Now, if the shaft is made of cast iron, determine whether the shaft will fail if engineer has fixed safety factor of 0.2. If the shaft is ductile and ductile material is used, will the shaft. Okay. What we're going to do is that we're going to do this one first, 1B. We're going to do 1B and then we're going to do 1A. Okay? Okay? We're going to do 1B and then we're going to do 1A. So we're going to do the ductile first. Okay? But still, we need to do this calculation. Correct? We need to do this calculation. Okay? What is the basic calculation? Finding what? Finding sigma B. Okay? Sigma bending. Okay? So given that sigma bending, right? Given that sigma BE is equal, alamak, it's not as easy. Sigma B is what? Sigma BE is 350, correct? 350. Sigma AX is equal to 180. And then you have tau XY is equal to 100. Okay? Okay, now take a look at the notes. Take a look at the note just now. Okay, DET. Okay, you can find, if you want, you can find the principal stress using this equation. Okay, can find the principal stress. First of all, you have to find this one. Okay, so if you want, you can find the principal stress. Where is this? This one. Okay, you can use this one. Okay, or for round beam. Where is it? For round beam. This one. Okay, this is to find the principal stress. Okay, the principal stress, or you can use this one. This one. Okay, you can use this one. Okay, so you can use this one. This is to find it. But to do this, you must find the sigma 1 first, and then you have to find sigma 2 first, and then you can find sigma prime. Okay, sigma prime. But if you use this equation, straight away you can use it. Sigma prime is equal to sigma x squared plus 3 tau xy squared. Okay, so that's what I'm going to do. Okay, so sigma prime is equal to sigma squared plus 3 tau xy squared, square root. Okay. Okay. So right now here, You stop there. Okay. This is sigma BE. This is sigma BE. This is A. Okay. So this is sigma AX. Correct, nah? This is sigma AX. And then this will be tau. It will be tau. This will be tau. Okay. So what we have here will be sigma squared. Now sigma squared, there are two of them. Okay. So here you must add the sigma BE plus sigma AX. Sigma BE plus sigma AX is equal to 350, 0, 0. So you have 0. 8 plus 5 is 13. Correct. 3 plus 1 plus 1 is 5. So you have 530 squared plus 100 squared. That will give you a value of, what value give you?
557.58.
557.
0.58.
557.6 lah. Okay. If you see I do like this, right? Okay, it means that dot, because I cannot, the dot doesn't work with this pen. Okay. So 5.76 MPa, right? Okay. So based on this, you already got the von Mises stress. This is the von Mises stress. So what you do is safety factor is equal to okay. What is this? Wait, why? No, go back. Oh yeah. What happened? Did I press something? I must have done some full page. Never mind. I do not know how to change it later. Okay. Safety factor will be equal to SY. Escape. Okay. Safety factor is equal to SY. Okay. Okay, SY divided by sigma prime. Okay, so what is SY? SY is given, right? It's given, SY is given as, what's the value of SY? SY is 590 equal to 590 divided by 557.6. So you have something definitely greater than 1. So save. Okay, okay, or save. The design is safe. Okay, based on the DET. Okay, now do you need to do calculation for this one? Do you need, there is a C, correct? Not that C, right? There is C. So do you need to do calculation for C? Okay, well, if you have if you just make a judgment, right? You'll find that sigma BE here at C, the bending stress is negative. Correct or not? Okay, bending stress is negative. Okay, and because by virtue of sigma stress become negative, so this value, color different, this value, okay, by virtue of this one now sigma BE and sigma AM, this one will be negative. Sigma BE is negative. Okay, so will be minus sigma AX, correct? Sorry, this one plus, this one is minus. So obviously sigma here, this sigma will be smaller, right? Sigma will be smaller because it's now there plus and minus. Just now it's plus and plus. So now plus and minus, so sigma squared will be smaller. By virtue of sigma squared become smaller, then 557.6 also will become smaller. Okay, will become smaller, and say it's smaller, then you'll find that the safety factor will be higher because this one is smaller, so safety factor at C will be higher. So that since we are more concerned because one is higher, one is lower. You have two safety factor. Whichever one you take is the one which is lowest. Okay, the one which is lowest is your answer. So obviously at C, safety factor will probably be around like what maybe 2, right? Maybe like 2. You can do your calculation later and you find it's a lot higher than at A. Okay, so we'll say the safety factor is equivalent to 1 point something. It is 590 divided by 557.6. So that will be the answer as far as concerned when it comes to DET. So the shaft will survive the load. Okay, the shaft will survive the load. That is based on DET. Correct? Okay, now we are going to try to find. Okay, now DET finished. Okay, and as you can see, the calculation is quite short, very straightforward. Okay, so you should be happy about this. But after this, you're going to do the MNST, which is the first question. Okay, now you find the first question is more complicated. It's long-winded. Okay, so I'm going to take away this one. I'm going to take out this one. Okay. Okay, so you have this value. Okay, now we are going to do the MNST. Now MNST, right? Because you see, as the reason why it's longer, as you can see that you have different SUC and different SUT. Correct? Okay, so I come to the brittle material. SUC and SUT are different value. Just because of that, you have to do separate calculation for A and C, and they must be done separately. And then later you have to compare the safety factor. Okay, it's very important. Okay, for DET now there is only SY, so the calculation is very short. Okay, but now for this one it is different. Okay, for MNST, first of all, what you need to do is to find sigma 1. Okay, now okay, for this one, for the first one at A, so you'll find that for principal stress, sigma 1 is equal to sigma x squared, and sigma x divided by 2 plus, correct, sigma x squared divided by 2, sigma x divided by 2 squared plus tau x squared. Okay, and you'll find that the value here will be, okay, 548. I've done the calculation. Okay, 548 MPa, because it's going to be quite long. Sigma 1. Okay, for A. And then you have to find sigma 2. Okay, now sigma x, okay, let's put this one first. Sigma x is equal to 350 plus 180 equal to 530. Is it 530, right? Right, 530. So this is sigma x, so you get 548. What about sigma 2? Then you have sigma x 2 minus sigma x divided by 2 squared plus tau x y squared. Okay, so it's equal to, by calculation, I get this value as minus 18.2 megapascal. Okay, so that's why I said when you do this, you will get one positive, one negative. So what you have to do now is do your simple equation. So safety factor is equal to SUT divided by sigma 1, okay, will be equal to safety factor SUT. What's the value? SUT is 1430. 1430. Sorry. SUT is
680.
680. 680 divided by sigma 1. What is sigma 1? 548, right? 548. So you get the value is what? What's the value?
1.24.
1.24. Okay. And then what you do is SF again is equal to SUC divided by S2. Okay. Take note, be very particular. Sigma 1, we say SUT divided by sigma 1. Is it possible that SUT equal to sigma 3 or sigma 2? Or it's possible? Because why? It is possible that sigma 1 is compressive and sigma 1 is compressive, sigma 2 is tensile. Okay. So one tensile. So you must compare tensile with tensile, compressive with compressive. Okay. Don't do the reverse. Okay. Compare tensile with compressive, then the answer is wrong. So we use sigma 2. As you see, sigma 2 because sigma 2 is also compressive. Okay. So you have this one. As you see, is equal to 1430 divided by sigma 2, which is 18.2. Okay. So you have a choice. If you want to put negative here, you can put negative here and negative here. Okay. If you don't want to put negatives, okay, but it doesn't matter as long as you are aware. Okay. Okay. So the answer will always become positive later, right? So what will safety factor you get? This is around
78.57.
78. Okay, 78.5. Okay. Now, so which one will you select? You select 1.24 or 78.5?
1.24.
Yes, always pick the smaller one. Okay. The one that is smaller is the answer. Okay. So as far as you're concerned, safety factor of the design, as far as the element A is concerned, is 1.24, which is it safe? When we consider what will be the safety factor limit given by an engineer, 1.2, isn't it? So if the safety factor, the engineer said that safety factor has to be 1.2, right? So it means that you get 1.24, the design is safe. Yeah, design is safe. Correct. Okay. So now once you have finished this one, then you have to do the other one. Okay. So that's why you need to do C. Okay. Unlike DET, because SY is the same, okay, for both A and C, so you only consider one of them, whichever is the higher. Okay. Now for this one, you have to do calculation for C also. Okay, for C individually. Okay. So cannot. Okay. So what happened is here, you have to do your calculation here. So now this one is different. This is negative. So what you get will be negative 530. Okay. So what's the answer? Is it correct? 350 is bending, right? 350 is bending, right? Okay, that's correct. Okay. So now bending, because as you know, bending there is always positive. Do you know why this one is negative 350? Do you all know why negative is 350? Come on. Do you all know why negative this 350 is negative and no more positive like before? Come on. Anyone?
It's compressive.
It's going backward.
No, this is by virtue. Okay, let's take a look. Okay. Luckily, if you look at this one, you look at this one. Okay. So this one is bending like this. Correct or not? It's bending like this. Okay, bending like this. So obviously, because it's bending like this, right? Like this. So A, right, will be in tensile. Correct or not? It will be stretch out. Can you see it? Okay. There's a beam, right? You hold your pen, you hold your pen pencil. You have to press down. Then the one at the top will have to endure tensile stress. At A will be tensile. Correct? So like this. Right? So here, because you have divide by 2 here. So here will be compressive. Why? Because this part here is being pulled down. Okay, so it's become like it's like this. Okay, and what about this one? This one is compressive. So at C is compressive. So that's why at A, okay, at A, the element is like this for bending. At A. At C, right, the element is like this for bending. And whenever there is bending, there will always be positive and negative, okay, or be tensile. Okay, when there is bending, there must be tensile, there must be compressive. Okay, any question? Do you understand what I'm explaining now? Are you all okay?
Okay, doctor.
Yeah,
Doctor.
so you understand. So A is tensile. So the stress at A, bending stress at A is tensile, bending stress at C is compressive. Okay, by virtue of this. Okay, so remember, when there is bending, there must be positive, there must be negative. Okay, if you forget one of them, you may fail. Okay, so this one is because at C, bending is now negative, so minus 350 plus 1 is 0. So who have calculated this one? Anybody calculated this one?
170. Negative. Negative 170.
Negative 120.
170.
170. 170. Okay? Negative 170. Okay? So by virtue of this one, this value also change. This value also change. Okay? So now virtue of this one, if I'm not wrong, my calculation said that now it is 46.2. This one now is 46.2. Is it? Is it? Can you verify? And this one is minus 216. Or is it opposite? Okay, so you have this one. The one at the top is 46.2 megapascal tensile, and then at sigma 2, okay, you have sigma 2 equal to minus 216. Okay, so this is what happened because this one now you have to consider C separately. So now you have to do this one. So SF here, SF will be equal to now we 680 divided by, remember, 46.2, okay, equal to berapa? How much? How many? SF now will be equal to minus 14. 14
14.
14 something lah. Okay, this one will be equal to what is where is it? 1430 divided by minus 216.
3.15.
3?
Yes.
3 cannot be 3. 2 times 3 is only 6.
6.6.
6.6. 6.6. Okay. So that should be the answer. So which one we use? Is it 14 or 6.6?
Value 6.6.
6.6. So 6.6 is smaller. So the safety factor at C is 6.6. Now, because C and A is just one whole piece, so we have to compare now the smaller one at C and the smaller one at A. Smaller one at A, the value is 1.24, which is smaller than the smaller one at C. So obviously, safety factor is 1.24. So your final answer will be safety factor is equal to 1.24. So your final answer overall, okay, is equal to 1.24. Final answer. So the design is safe based on the stress and also on the material applied.
Doctor, I have a question.
Yes,
Why we choose the smallest amount for safety factor?
because because the one that is smaller is the one that is going to break first. The one that will be fail first will be the one that's smaller. Because let's
Yes.
say 1.24, if we were to reduce all the value of safety factor from 1 to 4 by like 2, right? 2. 1.24, you minus by 2, you get what? 0 point something, right? Not? Because why?
Yep.
1.24 is very close to 1. So in other words, it is the one that will fail first. Okay, the smaller the safety factor, the more likely it will fail.
Okay, thank you, Doctor.
This is a fact lah. Okay, to argue this would be quite silly lah. Okay, the smaller safety factor means that the loading is higher, correct? Not holding higher, or the strength is lower. Okay, so by virtue of this, the safety factor you must always select the smaller one when you have so many safety factor. That is the one, because why? The one that is 78.5, we know that part will not crack. Okay, the one that is 6.6, that one will not crack at 14. So what happens is, let's say, if I were to increase the load, okay, the load is what is the load just now is 180, right? Let's say the what is actual stress is 180. If I were to gradually increase the load, okay, if I were to gradually increase the load, then the safety factor at A 1.24 will become smaller and smaller and smaller until it reach 1. Correct not? Whereas the rest still, okay, is very high, 6.6, maybe reduced to 5. So no problem. The one is 14, safety factor maybe reduced to 10. Big deal. Still safe. The one that is 78.415 or maybe reduced to 50. Who cares? Safety factor 50. Who cares, right? But the one that safety factor 1.24 reduced become 1. Okay, now it's critical. If you were to increase the load a little more, what happened? 1.0 will reduce to 0.9. Okay, it means that the design failed. What about the rest? The rest will drop a bit, but they are still very, very safe. Okay. Any questions? So basically, the most difficult part is not the design part. It's your nemesis. I call your nemesis. What is that? Your solid mechanic. Okay. How you calculate finding sigma 1, how you calculate to find sigma 2. Okay. That is your problem. Okay. And that problem actually is your solid mechanic problem. Okay. It's not actually related to me at all because I only do the design part. Okay. So if your solid mechanic is good, you'll find that your design marks will be very high. If your solid mechanic is very weak, then you will struggle in design. Okay. And no problem. You can still pass, I think. Okay. So not many people fail. Not more. Maybe like my class time, maybe 2 or 3. 2 or 3 will fail. Okay. And that is because they are too lazy. Very obvious lazy. Okay. They don't do the project properly or something like that. Okay. Okay. So now you have done a good job. You have solved problem number 1. Okay. Now we have another one. Okay. What is the other one? This one. Why is so stubborn? No? Oh yeah. Yeah, this one. Remember this one? Anybody say I don't remember means they have not done their homework. Okay, this one. Okay. So I think it's a good exercise for you to try. Okay, I've given you a lot of this solution. Okay, now I'm not going to discuss with you in length. Okay, how to solve this one. This is okay. So but anyway, just go through now to find P1 and P2. You need to find P1 and P2, right? So what you have to do now will be to calculate. Do your analysis looking from the side view. Okay, side view. Okay. Okay, so a side view, okay, then you have this one, okay, this one, okay, by virtue of this one, so eventually you get a value of P1 440, P2 416, okay, by virtue of this one. This is the equilibrium equation, summation T is equal to 0. Okay, as you know that when it comes to moment, you have moment X, moment Y, and then you have moment Z. Okay, when is it that moment become torque? When will moment become torque? When it is parallel to the axis of the shaft, of the rotating shaft. Okay, when it is parallel to the rotating to the axis of the rotating shaft, then the moment becomes torque. So T torque is either mx, my, mz depending on the axis of the shaft. Okay, so in most cases, T will be equal to mz. So T mz is essentially the torque. So here by equivalent of torque, sigma T equal to 0, right? So you do your calculation, you get P1, this equation, you get this equation, okay? Then you get P1 and P2, 1440 and 176. Torque is equal to 33. Okay, torque is equal to 33. So this one I've shown you, right? And then after you have that, you have to do this one. Okay, you have to do this one. Okay, this one is what you do in solid mechanic. Okay, it's just that when it comes to design, you have to do more. Okay, it is not so more difficult than what you do. Okay, the value is a bit complicated, right? But it's not so difficult. If you're careful, you don't make mistake. But you have to do more. Sometimes 2 times, sometimes 3 of them. Okay, so in this case, now you have to do the top view. So as far as concerned, you must draw based on the top view, what you see, the force acting from the top view. So this is what you see. I got class now. Salam. Okay, so what happened is that what was I? So what you do is draw the free body diagram like this. Okay, make sure don't make mistake. It's not so difficult, right? But you have to look at the diagram properly because you are seeing that in isometric, right? You are seeing them in isometric. So when you transform them into top view, you have to be very correct. Okay, and this is what you will get. Okay, this is what you will get, and then based on this one, okay, and what you are studying in solid mechanics, okay, you will get this one, this value, and you get this value. Okay, it's not something so difficult if you are familiar with your solid mechanics. Okay, so what you do is draw this one and then draw it. So this one is what, okay, in stress analysis for failure criterion, moment is very important. Okay, finding moment is very important because I said that moment is the one that is evil. Okay, in design is evil because why? It create the highest stress to any structure. Okay, so it's very important for you to find the moment. So here, what you do is find the moment. Okay, can you see that is minus 76.7 and this one. Okay, so all you have to do is this one, correct? Okay, so if you draw like this, okay, so the moment on this part here, the moment on this part here will be 225 times 300, correct? Not 225.4 times 225.4 times 300 will give you 67.6. Okay, will give you 67.6. Okay, so now to find the moment. Okay, so is it negative? I want to ask you, how do you determine whether the moment is negative or positive? If you can remember, anybody, how do you determine it is positive or negative? Anybody? Remember, if it's this shape, Is it positive or negative? If it's this shape moment, this is positive, this is negative. So this is if. So in other words, now if you were to look at this diagram, this part here, you take a look at this part here. Okay, you will see that AO will bend like this. Correct, no? AO will bend like this because why? 2 to 5.4 is going downward. Okay, the force is downward, of course. So O will also go down. So the shape will become this one. And this, because it's this one, it is this one. Okay, it's this one. Okay, so that's why the moment here is negative. That's why it's 67.6 negative. Okay, you have to be correct. Okay, the impact could be quite high if you get negative or positive wrong. What about this one? Now this one, what you do is do this one, and you find that here the moment here will be 1009.8 times 150 will give you 16.5. Now this one is positive. Why is it positive? Because based on this one, you'll find that the beam is bending this way. Okay, because of 10.9.8, the beam will bend this way, and of course you're talking about this one, and this make it positive. So you have minus 76 or 67.6, and then the at B moment is 16.5. Okay, how significant is this value? Is very important. Okay, what is the value of moment here? What's the value of moment here? 0. Okay, moment there. Okay, I put it that value, moment there, s equal to 0. I put it at x equal to 0. Okay, let's say you made a mistake and then 16.5, you calculate it, you think that is negative. This is negative. You calculate and then you see that wrongly and you think it's negative, so it become like this. All right. So now tell me, what is the moment here? Now, is it 0? No. Okay. The value moment is not 0. It's very high. Okay. Because of what you done, because of your mistake. Then if I were to ask you to calculate what would be the moment at this part, your value will probably be around maybe around 50. Okay. 50 megapascal Newton meter. Your moment is 50 Newton meter. Okay, by right, it is supposed to be 0. But because of your wrong calculation, okay, you say that is 50. And because of that, your design maybe will be a lot larger, okay? Will be extra safe. Why? You have included a load that shouldn't exist. You have included a load that shouldn't exist. And I mentioned you that bending moment create very high stress. So your design will have very high safety factor, which is not the right answer. Okay, so that is very important. You must be correct. So remember this one. Okay, you must remember. Okay, you must remember this one. Okay, don't forget this. Okay, now, okay, after you have clear, you have drawn the correct free body diagram and also the bending moment diagram. This is the bending moment diagram, correct? Okay, so now we go to this one is front view, top view, right? This is top view. Okay, so now we look at the final view. We have done the side view, we have done the front top view. Now we're going to look at the front view. This is the front view. Okay, what you see from the front, this is the loading. Okay, so similarly, you're going to find what is the value of OY, what is value of CY. Okay, and then you're going to draw this free moment diagram. Okay, so your moment diagram become like this. Okay, so you have moment as minus 84.6, this one minus 6, and then you have minus 23.1. Right? Okay, and then you have two value. Okay, so this is the answer. Okay, so you have this one. The final value will be this one. Okay, so at A you have from front elevation moment 84.6. From the plan is 67.6. Okay, from the plan, this is from front, this is from plan view. So at A, that is a moment. Okay, now at B 23.1, and this one at 16.5. Okay, there is a top of 33. Okay, now when you want to do your analysis for stress calculation, okay, you cannot do them for this one, for these two, for this one and this one, you cannot do them individually. Okay, you cannot calculate for stress at for 84.6 only and then do your calculation for 67 because why? This moment act at the same time. They act at the same time, so they must be calculated simultaneously. Okay, so how do you want to combine them together? Okay, how do you combine them? Because there are two different moments at different angles, so you have to find the Pythagoras value. Okay, find the Pythagoras value for them. So you have this one. So moment at A will be equal to this one, 84.6 squared plus 67.6 squared. Okay, so the answer will be, wait, I'm sure I calculated somewhere. So if I'm not mistaken, MA is 108.3. Newton meter. Okay, that is at MA. Okay, what about MB? Now MB will be equal to 23.1 squared plus 116.5 squared. Okay, this is basically Pythagoras, correct? So the answer will be 28.3. 28.3 Newton meter. Okay. Okay. So now you can proceed with your calculation. Okay. So at A, okay. So at A, sigma bending A is equal to, okay, this is a round shaft, correct? So if it's a round shaft, what can I do for this one? If you remember, I mentioned to you, what is 16, 32 M divided by pi d cube, correct? Okay, this one. Okay, so this will be 32 times 108.3 divided by pi d. What is d? Anybody know what's the value of d? 30 millimeter. Okay, is 30 millimeter, 30 mm cube. Okay, right? And then you have one more. You have sigma b bending at C, or wait. Just calculate first. C. We know that it will be lower. Just calculate. Okay. So it will be 32 to M. M will be what? 28.3 divided by pi d cube. Okay, pi d cube, and the answer will be 28 point. Wait. This is not 28. 28.3. Yes. So the answer here will be, okay. The stress you calculate. I've done the calculation, I think. So you have bending is 40.86. This one is 40.86, I think. Is it? 40.86.
Yes, Doctor.
This 40.86. 86. Okay. And then this one, well, no need to calculate lah, but right, okay. This one you want to calculate, you can calculate, but actually you know very well that because moment is lower, right? So it is not the critical region. But what you want to do is to find where is the critical region. So based on this, okay, sigma BE, you know that the critical region is at A. Okay, the critical region is at A. Okay. Okay, so this is the critical region. Okay, not at B, it's at A. So now from now onward, okay, if you are doing you now onward, okay, you write sigma BE. Okay, so you have sigma BE value already. Do they have sigma AX in this one? Do you have extra stress not in this beam?
No.
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 X by X kita zero, so life is easier. Will there be torque XY? Maybe you don't have to put torque XY lah. Okay. Let be older. Let be wiser. The tau will be equal to 16t divided by pi d cube. Okay. So 16t. What is t? T is 33. 16 times 33 kan. Okay, divided by pi 30 cube. Okay, so the answer will be 6.22. Okay, his answer is 6.2 MPa. Okay, so you have sigma BE, you have tau. Okay, you will have no sigma AX. So what you have to do from now is just to proceed what we have done in the previous exercise. Okay, previous exercise you have an extra sigma AX. Okay, in this one you do not have sigma AX, so the calculation is actually simpler. Okay, calculation is actually a lot simpler. Okay, so based on that, you proceed like just now. Okay, where is it? I hope I haven't did this time. Hope so. Okay, this one, right? First of all, find the DET. Find DET. Okay, find the DET sigma prime. Undo. Okay, sigma prime, DT sigma prime. Okay, and then get safety factor. Okay, safety factor will be is equal to SY divided by sigma prime, and then find MNST. Is it okay? Then you find that safety factor is equal to SUT divided by sigma 1, SF is equal to SUC divided by sigma 2. Okay, is both given? Yes. Okay, in this problem, okay, the S is not. Is it mentioned where? Is it mentioned? Is it mentioned? If it's not mentioned, remember that this is made of steel, made of. So in this case, SUT is equal to minus SUC. Okay, for this one. Okay, so all you have to do is look into your SAE 1015 HR. Okay, so what you have to do now, if you have to find, okay, you have to find this file. I cannot give it to you, right? Because it's taken from a manual. Material. Where is it? Let's see, I got it down. Yeah, is it here? Okay. Oh, it doesn't exist. Okay, sit there. Oh, it's not a valid file. Okay, big deal. So where is it? Have it here. Do I have it here? Chart and table. Okay, let's go for this one. Okay. Now, this is a book that you are supposed to use. Remember, when we are not under SOP, all right, this book is compulsory to buy because why? It's a open book test. So, if you were to you will need to come into class by the half of the semester, if happen, right, you still have to buy this book because the test will be conducted open book. So you must have this book. Okay. Now in this book, they have tables again. They have tables. Okay. So where is the table? This book, there is the table. Yeah. Okay. So this one is okay. This is table where it provide you with this the material. Okay, the material and the and their strength. Okay, here you see tensile strength, yield strength. So you have to look from the table. Okay, so if you look carefully just now, it was mentioned that the material is 1015 HR. So the material is SAE. Remember, if you check 1015, what is one? Yeah, so it's this one. See, 1015. Okay, so you have S roll, normalized, anneal. Okay, anneal is the one. If you remember from your material class, okay, anneal is the one that after being heated, they have gone through a special cooling period, cooling treatment. Okay, a very slow cooling treatment so that the material is will become less brittle and a lot tougher. Okay, and then normalized is normalized means that I forgot already. Normalized is less than anneal. Okay, I can't remember what is estrol. I forget. If I'm not mistaken, estrol means that it is as requested by the buyer. Okay, if a person requests for that shaft, okay, so most probably the buyer, okay, the person who purchased, the client, will do the cooling treatment themselves. Okay, so because of that, you as a supplier of the rod do not have to do any cooling. Okay, they just keep it aside, supply to them, let them do the cooling. Okay, so that is what I can remember. It's a long time. Okay, once I get more information, or you also can read through the internet. Okay, the different estrol, normalized, and anneal. Okay, so normalized will be more toward normal cooling. Okay, normalized means it is cooling through normal. So this one when you cool something in the air, okay, it cool by itself. Okay, so it's not what is under special cooling. Okay, it just let it cool by itself. That's normalized. Okay, anneal is a special one. Okay, special process like cooling. Okay, so that the material become tougher. Okay, and less brittle. Okay, estrol is as I mentioned, is a client requested system. Okay, so the client will request. They say they want to do their own cooling, so the supplier, you just give them the material, let them do the cooling. Okay, so normalized is the one that after you do your own, you just leave it in the air to cool by itself. Okay, it is definitely is harder. Okay, harder, but definitely more brittle. Okay, okay, so this will be the strength of the material. Okay, so here for SAE, the question say SAE 10.5. Okay, so 1015. So they mentioned HR. Okay, HR is a term used by a different manual. Okay, different user. So as far as concerned, just use normalizer. Okay, so yeah, if the word HR or cold drawn is mentioned, just use normalize. Okay, so SAE 1015 normalize. Okay, so the tensile strength is 424.0. 424.0. Somebody remember that one? Okay, this is MPa, and then for this yield strength is 324.1. Somebody write down? Okay, or if you have say 324.1 and also 424. I think I better write down somewhere. Okay, 424. Where is it? Where is it? Here. Where is this one? No, it's not one. This is one. No. This one. Oh yes. Okay. So here you have it's given that SUT. SUT. This one is equal to what? 420 is it? 420?
424.
424. 424. 424. And then SY is what?
4.1.
What?
324.1.
324. Okay. Okay, so 324. So that's it lah. So SF kita SY divided by sigma prime. Find your sigma prime. Okay. And then SF kita SUT, the SUT is equal to 424. And because SUT is equal to SUC, so in other words, this one is equal to minus 424. Okay. Is it okay?
Okay,
Oh,
doctor.
it's time, huh? It's time. Okay. So this is okay. This one. I think can you complete them? Can you complete them? And then you can submit to me on next class. I'll give you a lot of time, okay? Before next class, okay? Put it just before next class, give it to me, okay? Is it okay?
Okay, doctor.
Okay.
Okay, doctor.
Remember, after before class, not during class or after class. Okay. Some of you will always give me, sir, I have problem. Like nobody else has any problem, right? Okay. Before class. Okay. So I will put this as assignment for you inside the inside this portal, and then you submit through the portal. Okay. So in that way, okay, so the class is completed. So I will see you again on Wednesday, 2 o'clock. Okay. Any question before we part? Any question?
No, doctor.
No, huh?
No, doctor.
Okay. So if no problem, thank you very much. So don't forget, I'll put the question this one so that you can submit. Okay, you already have the question, but I will put them inside your portal so that you can submit. Okay, through the portal. Okay, I don't want you to fill up my Telegram with your sending. Okay, don't send it to my this one. There's so many. Okay, so it's full. I cannot go through everything, all of them. So please submit through the portal. Okay, so thank you very much. I will see you on Wednesday, 2 o'clock. Thank you. Assalamualaikum.
Thank you, doctor.
Thank you, doctor.
Assalam.
Salam.
Thank you, doctor.